In 2.6, the example average taps, average soda, we'll be calculating the least squares regression line using summary statistics. In lesson 2.5, we used tapping time to predict the amount of soda remaining in a vigorously shaking can. For these cans, the mean tapping time was 6 seconds with a standard deviation of 4.53 seconds. The mean soda remaining was 264.45 milliliters with a standard deviation of 12.92 milliliters. The correlation between tapping time and soda remaining was R equals 0.924. Calculate the equation of the least squares regression line for predicting the amount of soda remaining from tapping time. So if we're going to predict the amount of soda, that tells us that that's going to be our response variable or our y variable, and tapping time will be our explanatory or our x variable. It's always good practice to identify what you're given in the question first. So we'll begin by saying that the mean tapping time was 6 seconds with a standard deviation of 4.53. That's our mean of x and our standard deviation of x. Similarly, for our y variable, or the predicting amount of soda, we have the mean and standard deviation. So I identified these with proper notation. To determine the equation of the least squares regression line, we first need to calculate the slope. To calculate the slope, we're going to take our correlation and multiply by standard deviation of y over standard deviation of x, much like you've seen slope in algebra. So our correlation was 0.924, taking the standard deviations from above and dividing them, I get our slope to be 2.64. Next, we need a y-intercept. Since the line goes through x bar, y bar, we're going to be using that point to determine the y-intercept. So our average y was 264.45 milliliters minus the slope, 2.64, times the average x, which is 6, and that gives us our y-intercept. Putting this together, remember, statisticians like to write the line as y equals a plus bx. So putting that together, y hat equals a plus bx. We're taking our y-intercept plus our slope times x. For additional practice, please try exercise 5.